Okay, so I had a question that was asked to me by one of my students, and I just thought I would publish this just to clear things up. So we have a number of primitive types that we use in Java. So we've got the byte, the short, the int or the integer, the long, the float, and the double. We do have two more. We have Boolean and char, but those don't really apply to this because this is looking at the numbers. Now, with the exception of float and double, the remaining numbers are all whole number values. And they have a range. So these are the ranges for those numbers. So you can see that the byte is minus 128 to 127. The short is minus 32,768 to 32,767. The int is, well, minus 2,147,483,648, or 2,147,483,647. And the long, well, that's just a big ass number. Okay, so a float uses up to 7 decimal places and a double uses up to 15. This is 64-bit, this is 32-bit, 64-bit, 32-bit, 16-bit, and 8-bit. These are really important because these determine how much memory your variable is going to use. So let's go back to our list of variables here. Now, the interesting thing was that, well, there's 2 points I want to bring up really. The first one is when we use arithmetic. Now, as you know, we can probably do something very simple like add a couple of numbers. So what I'll do is I'll just output a couple of numbers being added. So if we do something like 4 plus 6 and we run this application, we should get, so we get 10. All right, so I'm happy with that. So that works. So let's minus it. So we should get minus 2. So let's just run that a moment. Yep, and sure enough, we get minus 2. Let's multiply it and see what we get. So we multiply it, and what do we get? Okay, so we get 24. Okay, what about dividing it? Okay, that's going to be the interesting thing, because this is what came up. So when we divide it, we get 0. And one of the questions I was asked is, why do we get 0? Well, the answer is we're dealing with 2 whole numbers, and whilst they're whole numbers, they do not carry a decimal point. So therefore, it's rounded to a whole number value. Okay, well, that's fair enough. Okay, so what we would need to do is convert one of these into a float, a number that will allow for decimal points. When we run that, okay, that's working fine. So I'm happy with that. And what we got 1, 2, 3, 4, 5, 6, 7. I did say you would get 7 decimal places, and sure enough, we have. Okay, that works. But why does it work this way? Okay, well, first of all, let's try this in a slightly different way. So I'm going to create some variables. I'll keep them as integers just to keep it basic. Okay, so num1. Now, arguably, you could make them a different value. That's fine. So we'll keep that integer as num1, and we'll keep the second integer num2 to equal 6. So we're using the same numbers as before. And I'm going to create an integer called total, which equals num1 divided by num2. Okay, to print the total. When we run this, the 0 will come back. That's fair enough. Well, what if I was to change this to a float? Okay, so it seems pretty happy with the values over here. So that's okay. We're now using a float over here, which has a decimal point, so that should work. So let's just run that and see what happens. And the answer comes up 0.0. Well, that's not right. We know it should be 0.666667. So why does that not work? Well, it's quite an easy answer when you think about it, really. If we look at these two numbers here. Okay. These are integer values. Now, the system needs to calculate these integer values before they can pass them over to the total. So before this goes into here, we have a couple of integers to deal with. So when we're dealing with 4 divided by 6 as integers, the value will become 0. When the value is then put into a float, the value is still 0. So as a float, it will just create it as 0.0. So what can we do to fix that? Well, we can go back to what we were doing before and convert one of these numbers into a float. So let's just do that a moment. So if I convert that to a float like so, we should get that 0.666667. So because I've elected the number to become a float, so zoom in again, this now is different because the value in here is now an integer. So we know that this one is an int, and we know that this one is a float. Because we're now dealing with an integer and a float, it's going to allow the float to work. Okay, one of the areas that I found that students were falling over is when they start dealing with big numbers. Now, if you ever deal with the Fibonacci sequence, that really does introduce some of those big numbers. So what I'm going to do is I'm just going to show you why that happens. So in this example, I'm just going to use the myInt. So I'm going to create myInt and give it a value. Now I'm going to give it a value just one below its maximum value. So 2147483646. Okay, so that's one away. And now what I'm going to do is going to create a for loop which will add one to that value. So let's just do that. So for. Okay, so for I equals 0, and I think what I'll do is we'll go around 4 times on this one. Print out of myInt plus I. Okay, space mat. Now when I run this value, an interesting thing happens. So we've got add 1 to this is 647. So this is a maximum number, but what happens is when it adds 1 again, it then becomes a negative value and remains negative. And if you look, it's actually going backwards now. Okay, so because it's adding 1 to a negative value, it is going backwards by 1. So the reason for this is it's just simply the way that 2's complement works. So as I said to you before, there is a difference when you're dealing with integer values. So just to show you what I mean. So if we're dealing with an integer value, we're dealing with 32 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we've got 32 columns there. That is what the maximum number looks like for an integer in binary. Okay. Now, if you take that value, okay, and simply add 1 to it, so just plus 1, what will happen is 1 plus 1 equals 1, 0, carry the 1. 1 plus 1 equals 1, 0, carry the 1, 1, all the way through up until you get to this other value, which is 1, and then all the zeros like so. Okay, now as I said to you before, the first value, this one here, is not really being used. It hasn't got a numeric value. What it is it determines whether the number is a negative or a positive. So when we add 1 to the value, it adds 1 to this number, and in binary generates this number. This number is the maximum negative value of a 32-bit number. Okay, so it's 1 followed by 31 zeros. So this becomes that negative value which we're seeing here. Okay, so negative 214,748,3648. Okay, and the reason why this one has gone up by 1 is because the next binary number that comes out would naturally be that number up there with 1 on the end. And that number is represented by this value. Okay, and if I add 1 on it again, this will become 6, 5, 4, 3, 2, 1 until you've got all the ones. Number that looks very much like, oops, not that, but like that. Okay, once we've got that value, negative 1. And then if we add 1 to negative 1, we get that, simply because we don't have a space, oops, on this side to carry the 1. So it just becomes 0, and it will then carry on as 0. So this will help you with the Fibonacci sequence. So what I would recommend is if your numbers are going to be much larger than the kind of numbers we would see here, so over 2 billion, I would recommend using a long for that. And that will then allow you to use a wider range of numbers. I hope you've learned from this and you've enjoyed this. And if you have, please give me a thumbs up and please subscribe if you want to be notified of any new material. Till next time, thank you.